All right, hello and welcome to lecture 6. Today's lecture is, I think it's very interesting. It's a nice way to wrap up what we've been doing in steel design so we can start a new topic starting next week. What I'm interested in talking to you about is how do you wrap up all the nice work and the design that you've been doing over like the previous parts of the course. What we've been doing so far in steel design. Done design of beams. Do you guys know how to design a beam? How to design a steel beam? Anyone can quickly summarize how to design steel beam? Yeah.
Calculating the moment, and then and the shear and all the forces, and then you find the moment of inertia. Select a beam from the table.
Yeah.
And then you have to check if this beam will support the weight, the moment, and the moment of inertia that you calculated to make sure if it's safe or not, or it's satisfactory or not. So then you have to calculate the class for the flanges in the web.
Yes.
And then you have to calculate the
You're going through a lot of details, which is excellent. Like when you're designing something, you need to be detail oriented. So if we can just like summarize it, like in 3 steps, how to design a beam in 3 steps. Find the load. Yeah, you definitely need to find the load. Then what? What's that?
Then choose the section.
Then choose the section.
Then validate if it will carry the load and hold the moment and
Yes, then make sure that the section is valid and is strong enough. What are the 2 limit states that you designed the section for? Ultimate limit state, make sure that it's not going to fail in bending or shear, and service limit state, make sure it's not going to deflect too much. Excellent. All right, so now you're trying to design a very interesting building that looks like this. You've designed some beams, you've designed some columns. Now it's time to bring it all together. How do you connect your beams and columns and bracing and all the elements of the structure to make it hold together? Otherwise, you're just like have a bunch of like scattered beams and columns. How do you bring them together? Yes.
You have 2 ways of connecting, or I think 3. It's either you bolt them and you're using bolts and connection plates.
Yep.
Or you weld it.
Yeah.
And there's a 3rd one, I don't remember. So
What is the 3rd one? How do
I
you?
remember last year we had like 3 in the presentation or whatever there was.
Yeah.
In the project, but I don't remember what the 3rd one is.
Okay, if you can remember, like you can bring it up. I am curious if you can think of any other way to connect steel members together. How do you connect a column with a beam? You're absolutely right. Anyone can think how to connect a column with a beam. Any thoughts? Can I get any contributions, ideas how to design a column with a beam?
Plates at the end of the beam.
At the end of the beam, you put a plate.
Yes, with some holes.
With some holes.
Yes, for the holes, maybe they are put together if it's fixed or
Yes, so you design the connection, fixed or pinned.
Yes.
And then what do you do with the column? Holes in the column, align the holes and bolt them? Yes, that would be a very valid way to connect these steel elements together. So you've designed a column from an I, you've designed a beam from a C channel, and you want to connect them together. You can connect them either using bolts. So you add these additional plates to facilitate or accommodate the connection, and align holes, use certain diameter bolts, and connect them together. You can also weld them. You can also weld the 2 members together, and this is something very specific to steel. Because steel is like metal, you can use welding on it. You cannot very easily weld other types of materials. So for steel, because the two members are made out of steel, you can actually use very high heat and melt the interface and create a weld. It's also very strong. So you can use both. If you look closely, you'll see that this plate in the connection is welded at the top and it's bolted at the bottom. Can you think of a reason why you would have a connection that will have part welded, part bolted? It's a very interesting and very practical reason. Why would you have a connection that has both?
If the thickness is very low, we cannot have the place for the bolts and the bolts of the bolts.
Yes, that's a good point. It has to do with the limitation of each side or each method. Some welding, for example, has limitation with like the thickness and the look and the finish, how you want the connection to look, and bolt as well, bolted connections as well. I'm curious if you can think of another reason. There's a very practical, very important actually reason why would you use bolted and welded connection or details in the same connection.
Because it depends on type of support you want to create.
Type of support, you want it pinned or joint. You can create pinned or fixed with both. You can create a fixed or pinned with both. It depends on the
Cost?
length. I just want to follow up with this saying like maybe welding is not going to be good with like allowing for rotation, because if you let it to allow, that might cause problems. So maybe bolted connection would be much better for pin connection. The idea I wanted to share with you is this has to do with how steel structures are fabricated. Usually before you do construction, the structure is made into pieces in a fabrication shop, and then it's shipped to site, and then it's assembled on site. Unlike concrete. Concrete, you can mix the concrete on site and pour it in the formworks. It's a very different way of erecting or building up steel structures. So what you want to do is think it through. Which parts of the building are going to be made in the shop, and when you ship them on site, how they're going to fit together. So maybe you want to create a connection that has this plate welded to the beam as one unit, and then you ship it to the site. When it comes to the site, a crane will pick it up and then align it in place and then use the bolts. So you use what's easier for you. Welding is much easier in the shop. As you're gonna see when we talk about how you actually weld something, it depends on the welder. There's a lot of experience, a lot of training that goes into mastering the skill of welding. If you're comfortable, if you're indoors, if you're in controlled environment, you will create a good quality weld. If you're hanging on a beam and you're scared for your life and you're trying to weld something upside down, most probably the weld quality is not gonna be good. Unlike the bolts. The bolts, you just pick the right grade or the right strength of a bolt, and you use wrenches to tighten up with the exact same torque that you desire, and you can apply it in an easier way on site. Before we get into like how you actually design a connection and what goes into it, I want to expose you to some examples. How steel structures look during construction. This is Faculty of Architecture or College of Art in Toronto. So they are the Faculty of Art, and they wanted to create a very interesting looking building, and the designer came up with this box on top of the building. When you get very interesting and crazy types of architecture like that, steel is usually a good application. If you want to build it from concrete, it's going to be bulky, very heavy. It's not going to give you that interesting look. So during construction, this is what happens. You need a tower crane to pick up the pieces, line it up, and this is how the connections look. These parts will come into pieces. You use the crane, you line them up, you use the bolted connection. This is how an inside connection looks like. That's how an outside connection looks like. And there is a fair bit of detailing that goes into it. Structure analysis 1, you'll probably remember we analyzed stresses. At the joint, we assumed it as a node, as a point. In reality, the intersection of the truss joint has big geometry actually. and you take into account how far you take the connection away and consider these plates, these gusset plates that hold the connection together. This is what I was talking about the construction process. Look at that guy. So this guy, hopefully, he has the health and safety precautions in mind, wearing harness, hard hat, make sure that if something happens to him in this vulnerable position, it's not going to be the end of his career and maybe the end of his life. This is interesting to keep in mind when you're designing structures. Keep in mind construction. Keep in mind the workers and people who are going to build it. Are what you're creating buildable, or it's too difficult, no one can actually line up the complex detail that you're doing. To make it as simple and easy as possible will make everyone's lives easier. Having said that, it's interesting to know the limitation and what can be done and what is difficult to be done. So whatever your role is, you're a designer, you are a construction engineer, you're on site, you're responsible for the progress on site. It's very important to understand what goes into bringing the structure together. Any questions so far? I have two examples here. This is an example of a bolted connection. You need the crane, line them up. The worker on site will install the bolts and tighten them. This is an example of a welded connection. This part is bolted. The rest of the frame is welded. It's shipped on site welded. So it's done in the shop. You see how this is welded in the shop, and then you send it on site, and very quickly, very rapidly, the building starts taking its shape. And it becomes these very interesting shapes, these very interesting complex shapes, because of the flexibility of steel that you can create interesting details and work around existing structures. Having said that, the role of connection design could make or break the building. You could have designed good beam design, good column design, then when you connect them together, the connection is not very good, and then the failure will happen at the connection. And the consequences could be catastrophic. I've talked about this example before. Maybe if you remember in structural analysis 1, I talked about an example of the consequences of a mistake in design. In this particular case, it happened in the 80s in the United States. The architecture feature in the hotel was a skywalk that connects the guest rooms from one side to the other, and the connection between the bridge and the tie rods to create space underneath the bridges were connected from the roof. These tie rods has a lot of tension in them. The original design was a simple rod, one rod going through the frame of the bridges. Along the way, the fabricator, the manufacturer responsible for fabricating pieces of the building and shipping it suggested a slight change in the connection. Long story short, this slight change was not looked into properly. And the consequences was loss of life, loss of property. It's a situation that you don't want to be responsible for something like that. The design of the connection is definitely part of the process. This is what happened. The original design was one straight rod through the two bridges. The proposed change was like, this rod is too long, we can't ship it on site. Can we break it at each level? Can you tell the difference between the top diagrams and the bottom diagrams? I'm curious if someone can pick the difference between the top diagrams and bottom diagrams.
The top one is only, there's a bolt, I think, from the bottom?
There's one bolt from the bottom.
Yeah. I can't see properly, but the triangle itself,
Yes.
the bolt connection.
And that's not the case in the bottom? Like, what's the difference between the top diagram and the bottom diagram?
On the bottom, there's two connections.
The bottom has two.
Connections, and the top only has one.
Yes, the top solution was like one bar through. The bottom solution, you interrupt the bar into two bars. You need to look closely at the design of your connection. The forces in the bar and on the washer, on the nut of the bolt, are completely different in the two cases. So that's an important thing to keep in mind. When I look at the structure, I have different levels of analysis. I can analyze the stability of the entire structure. If the wind is on the structure, is there enough supports and foundation to support it? And then I zoom in a little bit and I design a beam or a column. And then I can zoom in further and look at a connection. Are the bolts have too much forces, they're gonna break, or these forces are within the capacity of the bolts? Having said that, let's talk about bolted connections. So bolted connections means the connection is using bolts. What is a bolt? Yeah, this is pretty much what a bolt. It has like the head of the bolt and the shank or the length of the bolt. Part of it is threaded to allow for like a nut to lock the two pieces together. So what you do is you get two pieces of steel, you drill them both with a diameter slightly bigger than the bolt to fit it nicely, but don't drill it too bigger than the bolt, otherwise it will slip, the connection will slip. I want you to understand that the bolt could fail in the solid part or could fail in the threaded part, and the area is different. Can you think of a reason why the cross-section area of the bolt in the solid part is different from the threaded part? How do you create threads in a bolt? Do you know what threads are? Yeah, exactly, to allow for the nut. Why would the cross-section area be different in these two parts of the bolt? Yes, what would make it weaker? What would make this part weaker than this part?
This part is fully solid.
Because
This part is fully solid, this one is
because of the loss of area. That's how you create a thread. You machine it, you remove part of the bolt, and it becomes weaker in this part. So you will have like the gross area or total area of the bolt in the solid part, and an effective area that takes into account the threaded part. So just look closely at how the bolt can fail. Not only the bolt is responsible for the strength of the connection, the material itself could fail. So the bolt could be strong enough, but the steel could reach its limit, and the connection could fail in the steel. This is an example of something called like the block or group action. The individual bolts managed to withstand the load, but the failure actually happened in the actual connection, in the steel. So not because I chose a very strong bolt will guarantee a very high strength for the connection. You need to manage two things: the strength of the bolt and the strength of the steel. And the strength of the material could have different shapes. It could just like cut a straight cut in the material, or it could actually follow the pattern depending on the spacing between your holes. So when you create a connection, don't tighten up all the holes together, otherwise you create a very weak section. And most likely the force will just rip your section apart. We'll take that steel and rip it apart. So there are something called minimum edge distance and minimum spacing. You cannot put two bolts closer than a certain limit, and you cannot put a bolt closer to the edge than a certain limit. The code will give us guidance on that. Can you think of a reason why? Can you think of a reason why you cannot drill a hole that is too close to the edge?
area after the bolt, or the distance after the bolt, will be very weak that it will break.
Yes, I like that very much. So you can think of maybe a base plate. You want to connect that base plate to like the bottom concrete foundation, and this is the plate that takes the load of the column and distribute it for the concrete. The concrete has different strength than steel. Steel can take very high stresses. Concrete, compared to steel, can't handle that much stress. So you need the base plate to distribute the load. Let's say you want to drill a hole here to connect the base plate to the pedestal or the foundation. There is a limit to how close you get to the edge. That's called the edge distance. It's like the distance. You can't get closer than this edge distance. Otherwise, you can damage this weak section at the edge. At the same time, there is a limit to how close you can get to the column. Can you think of a reason why I cannot drill a hole and install an anchor bolt too close to the column? It's not going to be what? Balanced? Are going to be weak. So you're concerned about the symmetry? So there is a load here, and I'm questioning how close can this bolt be to the face of the column? Can you get too close to the face of the column, drill a hole, and install a bolt? What could happen if you get too close? It's just like a practical kind of installation issue.
You won't be able to screw it on properly.
Space to maneuver the.
Yes, yes. I like that very much. Because on paper, in theory, you might not find a reason why I cannot just like fit two bolts here.
But there won't be enough space.
But when you send it on site, you'll have a phone call from someone installing it. Will send you a picture of your design, and they will ask, how am I supposed to install this? You put the hole too close to the column, they can't fit a wrench or fit like something, a device to tighten up the bolt. So these issues are very interesting to keep in mind when you're designing something. Follow the code, follow the equations, and also think it through. Is it gonna work on site? Can people install it? Or you're gonna have problems later on. How do you analyze a bolted connection? A bolted connection is basically holding two plates or two pieces of steel or more. If it's holding two places of steel and there are tension forces, if there are tension forces in those two plates, can you guess what kind of forces these tension forces in the plates will cause on the bolt? So I have a steel plate to the right over here and another steel plate, and this is a bolt holding them together. I have tension over there and answer with tension over there. What are these two forces causing on the bolt? Is it causing tension on the bolt? Is it causing other stresses on the bolt? It's tensioning the bolt. So the bolt can take either tension force, you can apply tension on the bolt, or you can have shear on the bolt. You can shear the bolt. So when you have two plates like that holding the steel connection, these horizontal forces, what are they? They're trying to apply shear. Can you visualize how this plate and this plate is applying two opposite forces trying to shear off the bolt? That's the direction of shear. Shear is like perpendicular to the longitudinal direction of the bolt. You can have single phase shear or double phase shear. If the connection is holding more than two pieces, with one bolt. One direction will have two plates and the other direction will have one plate. When you pull them together, there are two shear planes. There are two shear surfaces. And then the force on each plane is like half the tension going into the connection. This is very important for the calculations because what you're trying to calculate is, let's say I have a simple beam and it has a reaction on the left. The connection between the beam and the column is a bolted connection. The beam is bolted to the column with bolts. So let's say I have space to create 4 holes, and in each hole I will put a bolt. So if the reaction is R, if the reaction of the beam is R, what is the shear force on each bolt in this connection? I have a connection that has 4 bolts. And this connection is at the end of a beam that has a reaction R. Reaction resisted by 4 bolts. What is the shear on each bolt? Yes, it's the reaction resisted by 4 bolts. And that's how you start analyzing the connection. You want to make sure that the shear on the bolt does not exceed the capacity of the bolt, and you also want to check that the steel beam web is not going to rupture. So that's the 2 checks you need to do. Before I leave that, this is how a bolt can fail in shear, and this is how the bolt can experience tension. You can have actually tension on the bolt, and it will it could cause tension force here on this connection. So the shear or the forces on a bolt can be either shear force trying to shear the bolt or tension trying to pull the bolt out of the connection. That's not the only failure that could happen in a connection. The steel plate could fail. It could fail in a bolt tearing or like rupturing. The bolt is still intact. It will just like rupture the plate, or the plate will be damaged in bearing. There are so much stresses on the point where the bolt meets the plate. It will exceed yield pretty much in this point and will have like a bearing failure. This is what we assume is going to happen when a bolt is trying to pull out of the connection, but in reality doesn't behave like straight lines like that. In reality, it will have like a cone shape. It will have like some angle. So which is going to have bigger resistance, the assumed failure shape or the actual failure shape? Which is going to predict a bigger failure load? Actual or the assumed shape? Assumed is going to assume bigger capacity?
The actual.
The actual? So I have 2 answers now. What makes you think the actual will result in bigger capacity?
Because it's taking more of the plate away.
Interesting. Yeah, you're on the right track.
In diagonal, so when it tears away, if it tears away in a straight line, that means that it's perfect flow, but actually there's loads of momentum.
Yes, that's a great answer. That's a very good answer. Any thoughts about this answer? Like, it seems like you wanted to say the assumed will result in a bigger capacity. Did you mean it's more conservative?
Yes.
It is more conservative because it's assuming that the failure shape will happen on a smaller surface. But in reality, the failure surface is bigger. That's why it's safe to assume that this is the failure shape, because in reality, we will have slightly a little bit bigger failure shape. All right. This is another check. The shear block or block tearing is that if you have a group of bolts tight up together, the connection could fail not only in the bolt or at a cross section, it could be the boundary of the group. It could be the boundary of the block. So this is a case where the block will tear on the bottom side of the block or the group and the end side and will cut the beam clean, or it will just rupture around the block. And the code actually shows us some example of cases that needs to be taken into account. I want to share with you how you can actually design a moment connection. We talked about how moment connections will fix the rotation, and it will provide bolts or welds, if it's a welded connection, above and below the beam. So how do you analyze a connection to resist moment? You just need to look at the forces on the joint. This moment will cause tension at the top, compression at the bottom. This tension will go from the flange to the connection, so it's probably going to cause tension in the top bolts, and the bottom will be resisted by bearing. The plate of the connection will bear against the column, so it's going to be critical to check the bolts in the tension side. So you break down the mechanism or the stability of your joint to figure out which bolts are facing shear, calculate the shear on each bolt, and calculate the tension on each bolt. And then check that the bolt can handle the tension or shear or both. What would you do if a bolt is experiencing shear and tension? Can you load it to its maximum capacity in tension and maximum capacity in shear? Probably not. So you will do the unity equation. Make sure that actual tension on capacity and tension plus actual shear on capacity and shear doesn't exceed 1. The ratio doesn't exceed 1. You can also need to do connections for other reasons. You can connect the beam to the beam and a column to the column. Why would you do that? Why would you connect a piece of a beam to another piece of a beam? Or why would you connect the column to another column?
The large span.
Yeah, because large spans. Because eventually, you cannot transport beams beyond a certain length. So you might need to do what is called a splice. So you can have a beam splice or a column splice. This is an example of someone bolting or installing a beam splice. If you look closely, there are no columns. It's just connecting a beam to another segment of the beam. This could be true also for the column. You can have a column splice as well. Any questions so far? Do you understand what is a bolted connection? Can you get the forces on the bolts? How do you get the forces on the bolts?
There is right reaction on the number of bolts.
Yes, so you need to count for the number of bolts. You need to figure out, are these forces shear or are they tension or both? It depends on, is it a moment connection? Is it a shear connection? Is it a tension connection? These are all different cases that you might want to design a bolted connection for. Let's take a look at welding. That's the second option to connect two pieces together. Welding is more controlled and more favorable in the shop, in the fabrication shop. It's indoor, it's under control, you have all the equipment, it's more comfortable.
Doesn't welding make the strength of the
That's an interesting question. That's a very interesting question. We'll get into it into a second. I just need you to understand the comfort of someone that is like upside down in the field or someone in the fabrication shop with all the tools with like straight up form. It will affect the welder quality of work.
In the field, it won't be 100% accurate. The issue.
Yeah.
You won't accurately weld both materials together.
Yes. Yes. which has to do with weld inspection. When you know that you have weld in the field, you need to get it inspected because there are some issues that could come up with weld. One of them is the quality or the craftsmanship of the welder. It takes training, and it's sensitive to the human factor.
Well, other than the training, other than the human factors, but doesn't أصلا welding like it takes time to
Yes.
like both materials. It needs other materials to keep it stuck together.
Yes.
It needs other materials.
So it takes time.
Other factors إن هو أصلا بتثبت 100%.
Yes, that's true. So this is the reason why I wouldn't be super excited about a field weld connection. I would rather have the weld in the fabrication shop and then any connections on site to be bolted for these exact reasons. So if you're responsible for a construction site, if you are designing a project, you need to understand what welding actually is. It's creating an arc, very high intense heat by using electricity most of the time. You don't need to actually touch the base material. Just when you get close to it, the difference in like voltage, the difference in like electricity will create an arc. Very high temperature will form, and then you will introduce the welding material, which takes into account about the welded section. How the welded section compared to the actual steel. Well, it depends to what you do to it. The material or the electrode that you use to create the weld material is usually stronger than actual steel. So failure usually is not going to happen in the weld, it's going to happen in the actual material. The fusion and the reaction is so strong. It creates a material, the welded material, that is stronger than steel. So the failure is usually, the material will fail before the welded section. Those are few different types. This one here is the very basic one. If you look closely, it needs just like a power source. The other ones need like a gas tank, and it's hard to take it with you on site. This one is more mobile. But the difference in the different types of welding has to do with many factors, like for example, the thickness of the material. You don't want to burn through the steel. The finished look. Some finished surface after welding will have like this slag, this material that will need cleaning afterwards. Some will leave with like a clean surface. It's easier to clean. And there are other types as well that are very good with thin plates, and it takes very good experience and practice to weld like nimble and small kind of details. So it depends on what you're trying to do. You're trying to kind of weld a big thick plate and it will leave that residue behind, so you might want to use one type compared to another. You're welding something that is very thin, maybe other types rather than steel. It takes more practice to use certain types than others. So what I want you to know is when you're specifying weld, so you're the structural engineer, you're producing structural drawings, you need to spec some properties of weld, at least to take it into account in design. So when you're designing a welded section, you need to know what kind of electrode they're going to be using. And you might want to leave a general note that use electrode with these specifications if you're welding. You don't have to go into too much detail. You probably will leave the responsibility of welding for the contractor. The contractor will provide a professional welder and they will be responsible for the work, but you also want to know what goes into it so that you can design it properly. If you weld something, you might want to reverse it. Welding is like you bring two pieces of steel together. What if you made a mistake? How do you fix your welding mistake? You need to cut it. You need to cut it. So similar to understanding ways to weld steel, you need to understand that you can cut steel as well. So those are different methods. There are methods that will use gases. You're probably familiar with like the two tanks mixed into a flame, and you can actually torch or cut steel. There are other methods that will use actually a power source, and for example, like the plasma arc will use like a combination of both. So how do you weld different pieces together? These are the two main types of welds. You can weld two pieces head to head. This is usually called a butt weld. Or you can weld them on a 90-degree. This is called a fillet weld. Fillet weld, 90-degree. A butt weld is like head to head. You can have no preparation for the original material. So do you see how these two plates, they have rectangular edges? Or you can bevel. You can see how the edge of this plate is kind of beveled. It has like a slight V shape to create more space, a pool, to accumulate the weld material. You create better welds this way. You can have a continuous weld. You can weld something continuously, or you can have intermittent weld, or like stitch weld, if you will. That works as well. You can save time. It's not going to cost that much. And it depends on what is the capacity that you're trying to get from that connection. If you don't need all that length of weld, you can divide it into shorter sides. Having said that, there is like a minimum length. You can't make a stitch weld shorter than a certain length. And the code will always give us instructions or guidance, really, on things like that. There is one thing that is very important to understand. What is the section, the weakest section in the weld? Let's say like you have a weld between these two pieces and it's trying to break. What is the size of the weld? Or it's called the throat length, the effective throat of weld. Where is that? Where is the weakest section in that weld?
Shortest distance?
It's the shortest distance. You will see that the shortest distance is the side divided by square root 2. It's like the shortest distance. So when you design a weld, you need to design the size for the throat, not the actual sides of the welds. I wanted to show you how you can weld, how the forces on your weld can be in two different directions. If there is tension in this plate, it's causing force perpendicular or transverse to the longitudinal direction of the weld. In a similar connection, but you're welding on the opposite sides, this force has parallel to the longitudinal direction of the weld. Do you see the difference? The code will actually provide slightly different way to calculate it, or will ask you, is your tension force alongside the length of the weld or perpendicular or transverse? So how do you know? It comes from like the layout of the connection. You sketch the connection. Are you going to weld it on this side or this side? Because it will make a difference. Very important. I want to add something related to the size of the weld. You can control the size of the weld. As a matter of fact, you will specify on your connection what is the size of weld, which is how you can calculate the effective throw. So how do you increase or decrease that size of the weld? Let's say I want to increase the size. I want to have the throat bigger. What would you do? Change the type of weld,
The voltage?
the voltage. These are interesting thoughts, but in any case, you cannot spend too much time or too much power on a certain spot at a time. You need to apply it in layers. So if you require a big size weld, you cannot do it on one pass. You just need to do it over layers. And that's what I mean. There is layer 1, and then you add layer 2 onto it, and then layer 3, rather than just spending a big amount of pool of weld on a certain spot. It will cause problems I will talk about in a bit. Do you have a question?
Won't doing the welding in different layers at different times cause it to be weaker? Because the connection between each weld, how does that happen?
Well, if you concentrate it longer, that will have bigger problems. So you're absolutely right. You need to prepare the surface properly before you go on the second layer. So you need to take into account the connection between the layers to avoid the problems I'm going to talk about. So you have your head in the right direction. Kind of be careful with the disadvantages of having multiple layers. Having said that, the opposite could damage the base material. So I want to show you some examples of how welding can go wrong. This has to do with like weld inspection. So you have specified weld, especially if it was field weld in the field, especially if that was an important structure. You welded a watertight structure, a structure that has water. So you might want a field inspector or a weld inspector. Their job is actually to go and check if there are problems with the weld, and usually they have like tools under their disposal to do their job. These are some problems that could happen. You can have a crack in the weld, longitudinal or transverse, or you can have a crack in the underbed or in the actual steel material. So you look for which kind of material is gonna fail. Too much heat, this is the point that we were talking about, will cause distortion. Remember the check for the shear capacity in the web in a beam? The design might dictate some stiffeners. These are the vertical plates that are stiffening the web. The web is usually very thin. If you apply too much heat on it, it might warp and distort like that. So that could be a problem from welding. I want to walk you briefly through how to design a connection, and then we can do the example in the tutorial. So the Eurocode has a very interesting way of providing or sorting out the content. Eurocode 3, part 1 is what we've been dealing with so far, is the design for bending, design for shear, for the structural element. Part 8 is for connections. So that's a different document from the one that we've been using. There are very important things I want you to take into account. The Eurocode will give us bolt classes. So these are classes for the bolts that we can choose from and specify on the structure drawings, and will guide us for the corresponding ultimate or yield strength. So if you choose a certain class of bolt, you can get from this table in the code what is the ultimate strength of the bolt and the yield strength of the bolt. There's a very interesting connection I want you to be aware of. This is something that has to do with designing trusses or designing hollow structures when you are taking into consideration the geometry of the joint. It's very interesting. We know how to calculate forces on trusses. we know how to make the assumption of all the forces meet at the joint. But when you're detailing it, you need to pay attention. Is the cross section or the center line of the members, do they meet all at one point, or there is an actual eccentricity? The diagonals meet at a point that has a different location than the center line of the chord. This will introduce some eccentricity that you need to take into account. These are the edge distances and the spacing that we talked about. The code will give us some guidance. Don't get too close to the edge. And there are also some guidelines on the spacing. And this is the block tearing that we talked about. These are some possible shapes that we need to take into account when we're designing a connection. This is the welding part. The code tells us where is the effective throat. It's the diagonal, as we talked about. And what if the surface has different shapes? It's concave or convex. Where would be the effective throat? It's very important to keep these in mind. All right. I think we'll have a better chance to go through the application of the equations when we take an example. But long story short, the code is trying to tell us what are the safety factors. Remember, like the gamma node, the gamma 1 and gamma 2. So when you're designing a bolt or a connection, it's not 1 anymore. It's 1.25. We need to figure out the shear capacity for like the material and the shear capacity of the bolt and compare the two. Like in essence, when you're trying to design a connection, make sure that the failure is not going to happen in the bolt and it's not going to happen in the base material. We can spend more time when we're doing the example. I have this in the lecture note, but we can spend more time to do it after we take a break. That's pretty much what I wanted to say today. Any questions? If you have any questions, feel free to come see me. If not, I'll see you in the tutorial. Let's meet back 15. 2:15, and I will see you there. See ya.